Have you ever stopped to wonder what's really going on behind the scenes of your favorite apps and websites? Because, there's this fascinating, invisible battle being fought every single millisecond, a fundamental puzzle that shapes your entire digital life.
Just think about it for a second. Would you rather have a service that is always 100% correct, but might just go offline sometimes? Or one that's always on, but might, every now and then, show you slightly old information? Now, this isn't some hypothetical question. This is a very real choice that engineers at Google, Netflix, and pretty much every major tech company have to make every single day.
And the reason they have to make that tough choice? Well, it's because of something called the CAP theorem. It's honestly one of the most important principles in modern computer science. And in this explainer, we're going to break down exactly what it is, and more importantly, why it matters so much to you.
Okay, so here's our game plan. First, we're going to uncover this impossible triangle that's right at the heart of the theorem. Then, we'll decode what those letters, the C, the A, and the P, actually mean. From there, we'll see how this whole thing forces an inevitable choice on system designers. We'll even explore the real-world trade-offs companies like Google are making, and this is the cool part. We'll discover how clever engineers try to cheat the system. And finally, we'll take a quick look at the next big challenges on the horizon.
All right, let's get right to the heart of it, this so-called impossible triangle, and why, in the world of big computer systems, you really can't have it all.
So this whole idea, it goes back to the year 2000. A computer scientist named Eric Brewer was looking at this new wave of massive internet services, and he realized they all face the exact same fundamental limitation. He proposed that any distributed system, which is basically just any service that runs on more than one computer, has to make a trade-off.
At its core, the CAP theorem is actually pretty simple. It says that any of these big systems can have three really desirable properties: consistency, availability, and partition tolerance. But, and this is the big but, you can only pick two. It's almost like a law of physics for the digital world. You just cannot build a system that guarantees all three at the same time. It's impossible.
So what on earth do these three letters actually mean? Let's break them down, one by one, because really, understanding these is the key to unlocking this whole concept.
First up is C for consistency. So what is that? It just means that everyone sees the exact same data at the exact same time. Think about your bank account. If you deposit money and then immediately check your balance from another device, consistency is what guarantees you'll see that updated amount. The system's job is to make sure nothing bad, like showing you the wrong balance, ever happens.
Next, we've got A for availability. And this one's pretty simple. It just means the system is always on. Whenever you make a request, you get a response. Back, every time. Think about doing a Google search. You expect it to work instantly, right? Availability means that eventually, something good, a response, is gonna happen. It doesn't promise it's the absolute latest, up to the millisecond information, just that the service is actually up and running for you.
And finally, there's P for partition tolerance. Now, this one is kind of different. It's less of a choice and more of, well, a reality you have to accept. It means the system has to keep working even when different parts of it can't talk to each other. I mean, the internet is messy, right? Connections drop, cables get cut. Partition tolerance is all about accepting that the network will fail and then designing a system that can actually handle that.
So, since we absolutely have to assume that network partitions are gonna happen, we have to choose P. The real, honest-to-goodness trade-off is always between consistency and availability. Let's walk through how a system gets forced into making this choice.
Okay, so here's the crucial moment. Imagine a network failure splits your servers into two isolated groups, Group A and Group B. They can't talk. Now, a customer sends a request to update their data, and it hits Group A. Well, now Group A can't tell Group B about this update, so what happens when another customer asks Group B for that same piece of data? Group B is stuck. It has a choice. It can either wait, maybe forever, until the network is fixed, which means sacrificing availability. Or it can just respond with the old data it has, which is now wrong, sacrificing consistency. It cannot do both. That's it. That's the choice.
And look, this is not just some theory. This exact dilemma plays out in the real world every single day, and it shapes the design of the services you use constantly. So let's look at a couple of real-world examples.
So here you can see the two main strategies in action. On one side, you have systems that choose consistency and partition tolerance. A perfect example is a system inside Google called Chubby. It manages really critical stuff, so for them, correctness is everything. If there's a network glitch, parts of that service will actually become unavailable rather than risk using the wrong data.
But then, on the other side, you have systems that choose availability and partition tolerance. Think about Akamai's web caching. Their whole job is to deliver images and videos to you as fast as possible. They will always serve you something, even if it's a version from a few minutes ago, because for delivering content, speed is way more important than perfect up-to-the-second consistency.
But what if you don't want to make such a brutal black and white choice? Well, this is where it gets interesting. The smartest engineers, they don't just pick two and give up. They get clever. They find ways to work around the theorem's limitations.
The big secret is segmentation. And honestly, this is a huge shift in how people think about system design. You move away from having one rigid rule for the entire service, and you move towards a much more nuanced, smarter strategy. Instead of making one big choice for the whole shebang, you break the system into smaller pieces, and you let each piece make its own cap trade-off.
And you can do this in a bunch of different ways. You can partition by the type of data. Your billing info. It has to be perfectly consistent. But your recently viewed items, that could be a little less strict. You can also partition by the operation. Clicking Buy Now absolutely has to be consistent, but a simple product search can lean towards availability. Or you can even partition by user, which is what Craigslist does. They have separate data centers for the East and West Coasts to keep all that local data super fast and consistent for local users. It's pretty smart.
So, the CAP theorem has been this guiding light for over 2 decades. But the digital world never, ever stops changing. And with that constant change comes a whole new set of challenges that are pushing the boundaries of this fundamental trade-off. Today, designers are grappling with some really big new questions. Like, how do you possibly maintain consistency when your service is spread across thousands of servers? Or how do you handle a malicious attack, which is way worse than just a simple network partition? And how does all of this thinking apply to the incredibly unreliable and unpredictable world of our mobile phones and wireless networks? These are the next big frontiers of system design.
So you see, the CAP theorem isn't just some abstract idea for computer scientists. It's a mental model for understanding your own digital life. The next time an app is unresponsive or a website shows you content that's just a little bit old, you can actually diagnose what's happening. It's not a bug, it's a feature born from an impossible choice. And now you have the tools to ask, which choice did its designers make and why?